Dear viewers, welcome to the UGC lecture series in biophysics. Today we are going to deal with hydrogen bonds, an important topic in biophysics. We are also going to consider the following objectives, namely what is a hydrogen bond and what are all the various perspectives of hydrogen bond, what are the properties and classification of hydrogen bonds, and finally the importance of hydrogen bonds in deoxyribonucleic acid and protein structures. Hydrogen bonds are a special case of dipole-dipole attraction, and this type of bond is stronger than van der Waals interactions, but weaker than the covalent and ionic bonds. The larger the dipole moment of the donor hydrogen bond, the stronger is the hydrogen bond interaction with the acceptor. Also, strong hydrogen bonds occur if donor and acceptor atoms are highly electronegative. Hydrogen bond is an interaction between the hydrogen atom in a polar NH bond, OH bond or fluorine hydrogen bond and an electronegative O, N or fluorine atom. The high electronegative difference of NH, OH and HF bonds cause these to be strong forces than the van der Waals forces. Let us see what we mean by electronegativity. This is the tendency of an atom in a molecule to attract bonding pair of electrons to itself, form dipoles and thus form bonds. In other words, it is a measure of how strongly the atom attracts the electrons in a bond. If the electronegativity of an atom is high, then it attracts electrons. If the electronegativity of an atom is low, then it tends to give away electrons. Electronegativity differences thus determine the bond type and explains what is meant by polar bonds and polar molecules. The higher the electronegativity difference, the more polar will be the bond. If the difference in electronegativity is greater than 1.7, let us say, then it is ionic bond. If the electronegativity lies between 0.5 and 1.7, it is called polar covalent, and finally, if the difference in electronegativity is less than 0.5, it is a non-polar covalent bond. Now, let us see what I mean by dipole-dipole interactions. Dipole-dipole interactions are attractive forces between the positive end of one polar molecule with the negative end of the another polar molecule. It is slightly stronger than the dispersion forces. Molecules are attracted to each other in a compound by positive and negative forces. This is shown in the picture below. A hydrogen atom is covalently bonded to an electronegative atom like nitrogen, oxygen or fluorine. A lone pair of electrons on the electronegative atom is formed. Now, we have two pictures. The first one shows the hydrogen bonds in water H2O, and the second picture shows the hydrogen bond atom or hydrogen bond in ammonia. Now, oxygen is very electronegative. It has two lone pairs of electrons in water. Hydrogen bonds in water are weak attractions between the partially negative oxygen of one water molecule and the partially positive hydrogen of a different water molecule. If you consider ammonia, nitrogen is very electronegative and it has only one lone pair of electrons in ammonia. So, this shows the lone pairs where hydrogen is attached directly to the most electronegative atom with the conditions, namely there is a partial positive charge of hydrogen, there is partial negative charge on the electronegative atoms as well as at least one lone pair. Hydrogen is attached directly to the most electronegative atoms with the conditions that the partially positive hydrogen is strongly attracted to the lone pair and the interaction is much stronger than the dipole-dipole interaction. So, this is schematically explained in these figures. Hydrogen bond, when we talk about hydrogen bonds, we talk about the direction, length, angles and strength of these hydrogen bonds. A hydrogen bond possesses direction and is generally asymmetric. The bond length depends on the angle and length. Hydrogen bond length on the other hand decreases exponentially with the distance. We have shown a hydrogen bond in the picture in this projection, where an angle 162 degree is marked right. So, the red marks left hand side and right hand side are the donors and acceptors, which are electronegative atoms. The angle subtended at hydrogen is shown as 162 degrees. This hydrogen and the acceptor O distance is 1.88 angstrom. The donor and the acceptor distance is marked as 2.82 angstrom. Electron cloud will be distorted towards the highly electronegative donor atom, so that the thinly shielded positively charged hydrogen nucleus or a proton becomes strongly attracted by the electronegative acceptor atom. The hydrogen bond acceptors are electronegative atoms with at least one lone pair of electrons. Classical hydrogen bond donors are only those hydrogen atoms bound to an electronegative atom such as nitrogen or oxygen. Now, let us see the distance, direction, lengths and angles of hydrogen bonds. Hydrogen bonds are directional and are generally asymmetric. The bond length depends on angle and length. The strongest hydrogen bonds are linear, which means that the angle subtended at this hydrogen will be 180 degree or very close to 180 degree. Hydrogen bond strength decreases exponentially with the distance, which we have seen. It is only Moore and Windmill who were the first persons to mention the hydrogen bond in the year 1912 itself. Now, let us see various perspectives of hydrogen bond as per the definition given by different pioneers in the field, namely Pauling and Pimentel and McClellan. Pauling is an authority in the hydrogen bond. He has even written a textbook on theory of hydrogen bond. Pauling in the year 1939 mentioned that under certain conditions an atom of hydrogen is attracted by rather strong forces to two atoms instead of only one, so that it may be considered to be acting as a bond between these two atoms. In 1960, Pimentel and McClellan defined hydrogen bond as it is said to exist when there is an evidence of bond, and there is an evidence that this bond specifically is involved in a hydrogen atom already bonded to another atom. Both the definitions are perfect, and Desiraju and Steiner in the year 1999 they define weak hydrogen bond is an interaction donor bonded to hydrogen which is attracted towards an acceptor A, wherein a hydrogen atom forms a bond between two structural moieties D and A, the donor and acceptors, of which one or even both are of moderate to low electronegativity. So, Desiraju, based on his contributions to the hydrogen bond, in fact, he has written a textbook on crystal engineering. Thomas Steiner in 2002 in his review article on the hydrogen bond in the solid state has reviewed the literature with some numerical data that have been newly retrieved from the most relevant structural database, the Cambridge structural database called CSD. In fact, he has also published a book on the hydrogen bonds with this data. The eminent importance of the hydrogen bond for the structure and function of and dynamics of vast number of chemical systems, which range from inorganic to biological chemistry, is the reason for the long lasting interesting of it. Hydrogen bonds are involved in many scientific branches like mineralogy, material science, general organic and inorganic chemistry, supramolecular chemistry, biochemistry, molecular medicine and also pharmacy. Many aspects of hydrogen bonds in structural chemistry and structural biology can be readily explained with only minor modifications to the hydrogen bond between water molecules. Today, the hydrogen bond is a much broader phenomena than the earlier days. The classical hydrogen bond is just one among many, a very abundant and important one. There are hydrogen bonds that are so strong that they resemble covalent bonds of their properties, and there are also other hydrogen bonds that are so weak that they can hardly be distinguished from van der Waals interactions. The electrostatic dominance of the hydrogen bond is true only for some of the configurations, whereas for others it is not. The H dot dot A denotes H is not directly bonded to the acceptor. It is the distance, and it is not in all hydrogen bonds shorter than the sum of the van der Waals radii. For an X bonded H group to be able to form a hydrogen bond, X does not need to be a very electronegative. It is only necessary that X bonded H is at least slightly polar. Also, in H not bonded to the acceptor, the counterpart A does not need to be a particularly electronegative atom or an anion, but only has to supply the sterically accessible concentration of negative charge. The energy range for dissociation of hydrogen bonds covers about 0.2 to 40 kilocalorie per mole, and the possible functions of the particular type of hydrogen bond depend on its location on this scale. The important role of hydrogen bond is in molecular recognitions and the use of suitable robust motifs for the construction of crystalline architectures with desired properties. So, this is called crystal engineering in the terminology of Professor Desi Raju. Distance between the donor and acceptor atoms is considered as a bond length. Experimentally, bond length is in general shorter than the sum of the donor hydrogen bond length and van der Waals radii of hydrogens and acceptor atoms. The non-bonded distance dA has to be in the range 2.3 to 3.4 angstrom. A hydrogen bond is symbolically denoted by D bonded to hydrogen, then dot 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 acceptor. D is the donor, A is the acceptor. The donor is bonded to the hydrogen. Depending on the dA distance and angle subtended at the hydrogen atom, that is called DHA angle, these bonds are classified as strong, medium and weak. We will see the table in the next projection. A hydrogen bond can be within a molecule, if so we call it as intramolecular, or between the molecules, which we call it as intermolecular. The hydrogen bonded complexes are stabilized by electrostatic, induction and dispersion energy terms. The electrostatic term contributed by dipole-dipole and ion-dipole interactions gives hydrogen bonds. They are highly directional in nature. The following table gives the full details about this. So, this table details strong, moderate and weak hydrogen bonds in terms of the bond energy, bond length, namely the hydrogen non-bonded acceptor distance and the donor and non-bonded acceptor distance, and also the bond angle at the hydrogen atom. Now, these energies are given in kilojoules per mole, bond angle lengths are given in angstrom, everything. You call it as a strong hydrogen bond, it is mainly covalent. If the bond energy is in the range 60 to 120 kilojoule per mole, bond length H A is 1.2 to 1.5 angstrom, dA the hydrogen bond length is 2.2 to 2.5 angstrom, the bond angle subtended at hydrogen atom is 175 to 180 degree. You call it a moderate hydrogen bond, mainly it is electrostatic due to electrostatic interaction. If the bond energy is between 16 to 60 kilojoule per mole, this is lesser than this, and also the bond lengths are that HA 1.5 to 2.2. So, this will be larger than the previous one, and the donor acceptor distance is 2.5 to 3.2. So, this is longer than this. Then the bond angle will be shorter than whatever you have seen the linear case is 130 to 180. Last one is weak hydrogen bond. This is due to electrostatic nature. Here the bond energy will be lesser than 12 kilojoule per mole. The bond length, particularly the HA acceptor distance, will be in the range of 2.2 to 3.2. Then the donor acceptor distance will be 3.2 to 4.0, and the band angle subtended with hydrogen is 90 to 150 degrees. Now, let us see some properties and common classification of the hydrogen bonds. So, first picture shows a nearly linear. So, it is not exactly 180 degree at H, maybe 170 or to 180. Now, second is known as bifurcated. Here a donor is there, hydrogen is bonded, but this hydrogen is accepted by two acceptors, that is called bifurcation. There are two acceptors. So, DHA this way, then DHA this other way. Then this is also a bifurcation, but one acceptor, two hydrogens are there, DHA, DHA. Like that we have three center bifurcation. Generally, in CH pi interaction, the CH bond generally has a small dipole moment. The attraction in these two orientations comes from the interactions between the positively charged hydrogen atoms and the negatively charged pi phase of the aromatic system. So, let us see pictorially what we mean by the CH pi interactions and what are the various types of edge to phase aromatic interactions. Aromatic means it is a ring. From the center of the ring we have a bond. Okay. Suppose carbon is there in on the end of the ring, hydrogen is bonded, this is C H. So, this is pointing towards the center of this ring, right. So, this will be one plane, this will be another plane, this is known as edge to phase, this is called T shape. Now, in T shape there are different types, edge tilted T, phase tilted T, it is very clear from the picture. So, these pictures show the various types of CH pi interactions. Now, what do you mean by intramolecular and intermolecular hydrogen bonds? As we discussed before, intramolecular means within the molecule hydrogen bonds and intermolecular means between the molecules. If we have hydrogen bonds, that is known as inter. So, here we have intermolecular hydrogen bonds where a nitrogen atom is bonded to hydrogen. This is shared by the n of the other molecule, one molecule, another molecule, that is why inter we are talking. Okay. In some cases, let us say here, so this is n, h, n. So, same molecule, within the same molecule we have interaction, that is known as intramolecular interaction. Now, between this molecule and this molecule we have this N, H, O. As we have seen in the beginning, I told you crystallography we have a convention, nitrogen atom, carbon atom is black, nitrogen is blue and oxygen is red. So, this is the color code we are following. Within the molecule we have intramolecular interaction, between the molecules we have intermolecular interaction. These interaction hydrogen bonds are parallel, because like a description of a baby, once you solve a molecular structures we have to explain what are all the features of the molecule. There comes intramolecular and intermolecular hydrogen bond during the packing of the molecules in the unit cell. So, this is another molecule which has a packing like this. These are special features, no? It is having a wavy motion, no? A wavy motion picture is here. So, each structure has its own unique packing in the unit cell. So, this is known as NH2 hydrogen bonded dimer. Why you call it dimer? This is one molecule, this is another molecule. So, these molecules are linked by parallel hydrogen bonds. Nitrogen is blue, N, white is hydrogen, NH, O is red. So, one molecule, because the donor atom nitrogen and this hydrogen is shared by another molecule oxygen. So, this is acceptor, but the same molecule here it has a donor nitrogen, hydrogen, other molecule becomes acceptor. So, this is quite commonly found. We can have 4 molecules also, this is known as hydrogen bonded tetramer. No? So, between this and this we have interaction, between this and this we have interaction, this and this we have interaction, this is called tetramer. Now, sometimes we have NHO and CHO hydrogen bonded molecular ribbons going like that, then molecular sheets going like this. So, sheets. So, hydrogen bond goes like a sheet, this here it goes like a ribbon. It is a different features of the hydrogen bond. Now, what is the significance of a hydrogen bond? It holds 2 strands of the deoxyribonucleic acid double helix together, because whenever a molecule is there or a structure is there, it has to have a stability. That stability is given by the intramolecular hydrogen bond. Hydrogen bond holds polypeptides together in such secondary structures. It helps enzymes to bind to the substrates. Hydrogen bond helps antibodies to bind to the antigen. These are various functional uses of hydrogen bonds in structures. Hydrogen bond also contributes to structural stability and folding. It contributes to catalysis. It also contributes to protein ligand, protein protein and protein DNA interaction, which you will be seeing later in our lecture series. Now, let us consider the importance of hydrogen bond in DNA. Hydrogen bonds play a very prominent role in structural chemistry and also in structural biology. DNA, the deoxyribonucleic acid, is a polymer of nucleotide linked together by phosphodiester bridges. Phosphate group of one nucleotide bonds with the hydroxyl group of the following nucleotide, generating the single strand of DNA molecule. DNA double helix, which won the Nobel Prize, is made up of two polynucleotide strands intertwined together to form a long helical structure. Watson and Crick, they got Nobel Prize, they received Nobel Prize for discovering the DNA double helical structure. Let us see the importance of hydrogen bonds in the DNA. The two strands are held together and stabilized by hydrogen bonds between them. The nucleotide adenine, symbolically represented by A, pairs with thymine T and guanine G pairs with cytosine C. This we call it as AT and GC pairs. The pairing occurs through the hydrogen bonds. Two hydrogen bonds occur between AT and 3 between GC. So, let us see it in this picture. So, we can see here clearly two hydrogen bonds here in the AT, and in the GC we have 1, 2, 3. So, this is pictorially shown here. Here we cannot see that much clearly, and this AT GC hydrogen bond you can see it in the DNA double helix, which holds the two DNA strands together. So, this is exactly clearly given here. The DNA base pairs, two hydrogen bonds are here, the NHN and NHO, and here the three are shown here, NHO, NHN and NHO. So, here it is clearly seen. So, what are all the pairing nucleotide bases? Let us see what is the importance of the hydrogen bonds in protein structures. The function of a protein is determined by its three-dimensional structure. So, that is why in order to know the function using X-ray crystallography, we determine the structure of the protein using single crystal X-ray diffraction. Once you know the function, then once you know the structure also, we in turn determine the different types of bonds that stabilize the structure, and hydrogen bond is one of them. So, this is an essential feature in stabilizing the secondary and tertiary structure of proteins, and also in protein ligand interaction. Again, in depth we will be seeing it later. Secondary structure of proteins, namely the alpha helix and beta sheets, are created by the hydrogen bonds between carbonyl oxygen and amide oxygen hydrogen. Amide hydrogen means N bonded to H, carbonyl oxygen means C double bond O, that H is bound to this O. In the case of alpha helix, different types of helices are described based on the number of amino acid residues per turn, pitch and the distance per turn, which in general are decided by the nature of amino acids and the hydrogen bonding between them. The structure of alpha helix is stabilized by hydrogen bond between the hydrogen atom attached to the electronegative nitrogen atom of a peptide linkage and electronegative carbonyl oxygen atom of the fourth amino acid residue on amino terminal side of that peptide bond, which means that the donor is in the fourth position, acceptor is in the first position. Count the number of atoms lying within the bond, that will be 10, that is known as C10 bend. And famous Indian scientist Professor Balram from Indians of Science has contributed a lot in this type of hydrogen bonds. So, this is shown here also, these bonds are shown here. Beta sheet, what do you mean beta sheet? Every peptide bond participates in the hydrogen bond except those that are close to both the terminals. In beta sheets, hydrogen bonds are formed between adjacent segments of polypeptide chain. In beta sheet we have two types, one is known as parallel beta sheet, other is known as anti-parallel beta sheets. Anti-parallel beta sheets contain 10 to 14 atoms in a ring and the hydrogen bonds are linear. So, like this, right, other they will be parallel, whereas in parallel beta sheet 12 atoms are in a ring, hydrogen bonds are not at 180, because when it is linear you say angle subtended at hydrogen is 180 degrees. Now, therefore, these are parallel. Here these are not parallel, angle is not 180 degree. In beta turn involving 4 residues, the hydrogen bond is formed between the first and fourth residue, where the central 2 residues do not participate in the inter-residue hydrogen bond. though this causes a bending within a short number of residues. We talk about folding of a protein. In gamma turn involving 3 residues, the hydrogen bond is formed between the first and the third residues. And where are the other places you can find the hydrogen bonds? One is the protein ligand hydrogen bond interactions observed in molecular docking. So, what do you mean by molecular docking? There is a protein molecule, a larger molecule, which has a shallow region, and this shallow region may contain the active site residues which are responsible for the function of the molecule. When this protein is overexpressed or underexpressed, we want to control this function by binding a small molecule in the cavity, which will bind with these amino acids and control the function. So, this is known as docking. When a small ligand molecule binds at the active site of a macromolecular target, the hydrogen bonds play a major role. The amino acid atoms or the ligand atoms in the small molecule may act as donor or acceptor, and as we have seen already, for hydrogen bond what we need is a donor which is already bonded to hydrogen and an acceptor to receive the hydrogen. So, these donors and acceptors may come either from the amino acids residues of the macromolecule or from the ligand atoms. The donor or the acceptor atom can be either from the amino acid at the active site or from the ligand atom. According to Lipinski's rule of 5 in structure based drug design, there should not be more than 5 hydrogen bond donors and there should not be more than 10 hydrogen bond acceptors in a ligand. So, we will deal with this in depth when we talk about docking, molecular docking and molecular dynamics in the structural biology. So, this is the exact picture, clear picture of these hydrogen bonds, which are bonded to amino acids. When a ligand binds, so what are all the interactions? The dashed ones are all hydrogen bonds. So, in summary, we have seen that hydrogen bonds play an incredible role in providing rigidity to the 3-dimensional structure of small and macromolecules. The strength of the hydrogen bond is characterized based on the electronegative potential of the donor and acceptor atoms and also based on the distances and angle between donor, hydrogen and acceptor atoms. So, these are the following references and textbooks are there. Whenever you find free time, please go through them, and also the interesting original papers on hydrogen bond. So, this is a textbook written by Scheiner on hydrogen bond. Pauling also written a very big book, and it is outmarked 1963. This is the latest data are incorporated in 1997, the nature of the chemical bond, and of course, Pauling is the father of the alpha helix. So, we will discuss more in the next interaction. Thank you.